स्टूडेंट्स, इस तो पहला असी एटॉमिक न्यूक्लियस ਅਤੇ रेडियो एक्टिविटी बारे काफ़ी विस्तार नाल पढ़ चुके हाँ। ਅੱਜ ਦੀ इस क्लास विच साडा मुख विषा न्यूमेरिकल प्रॉब्लम्स बेस्ड ऑन न्यूक्लियाई रहेगा। हाँ, अगे चलन तो पहला ज़रा एटॉमिक न्यूक्लियस नाल रिलेटेड कुछ फॉर्मूले एक बारी रिवाइज कर लेंदे हाँ। इस नाल सानू प्रॉब्लम्स सॉल्व करना सौखा रहेगा। The nucleus has its own structure and consists of protons and neutrons called nucleons. According to Einstein, a particle of mass m possesses an equivalent energy E given as E equal to mc square, where c is the velocity of light. किसी एलिमेंट का एटॉमिक नंबर उस एलिमेंट के न्यूक्लियस विच नंबर ऑफ प्रोटॉन्स की गिनती होंदी है अते एक कैपिटल Z नाल रिप्रेजेंट किया जाता है। इसे तरह किसी एलिमेंट का मास नंबर उस एलिमेंट के टोटल नंबर ऑफ न्यूक्लियॉन्स की गिनती होंदी है अते ए कैपिटल A नाल रिप्रेजेंट किया जाता है। इथों ए रिजल्ट निकलता है कि एलिमेंट का न्यूट्रॉन नंबर n a माइनस z दे इक्वल होता है। टोटल मास ऑफ न्यूक्लियॉन्स इन द न्यूक्लियस इज कॉल्ड न्यूक्लियर मास। If m is the average mass of a nucleon, a is the number of nucleons, then nuclear mass is equal to m into a. Radius of the nucleus r is equal to r0 into cube root of a, where r0 is an empirical constant whose value is about to 1.1 into 10 raised to the power minus 15 meter. Nuclear density rho is equal to 3m by 4 pi r0 cube. Here m and r0 are constants. Therefore, density of nucleus is the same for all elements, which is equal to 2.97 into 10 raised to the power 17 kg per cubic meter. In a nucleus ZXA, mass defect delta m is equal to Z into mass of a proton plus A minus Z into mass of a neutron minus experimentally measured mass of the nucleus. In a nucleus ZXA, by using Einstein's mass energy equivalence, binding energy EB can be expressed as Z into mass of a proton plus A minus Z into mass of a neutron minus experimentally measured mass of the nucleus into square of the speed of light. In general, the binding energy per nucleon is the average energy per nucleon needed to separate a nucleus into its individual nucleons. Atomic number 82 तो उत्ते atomic number वाले nuclei अनस्टेबल होंदे हन अते स्टेबल स्टेट एक्वायर करन लई ए स्पॉन्टेनियस एमिशन ऑफ रेडिएशन कारण डिसइंटीग्रेट हो जाते हन।
When they break up, they also release an enormous amount of energy in the form of radiation. This type of radiation is known as radioactivity.
हैवी एलिमेंट्स दे न्यूक्लियाई दे स्पॉन्टेनियस डिसइंटीग्रेशन कारण इन्हां विचों सर्टन टाइप्स ऑफ रेडिएशंस दे एमिशन नूं नैचुरल रेडियो एक्टिविटी कहा जाता है।
Experimental investigations have proved that the radiations emitted by radioactive elements consist of three kinds, depending upon their ability to penetrate matter. One kind of radiations with least penetrating power is named alpha decay. Here, least penetration power means the radiation which would stop first. The other kind with a comparatively larger penetrating power is named beta decay. Furthermore, the last kind of radiation with maximum penetrating power is called gamma decay.
An alpha particle has 2 protons and 2 neutrons. It possesses double the positive charge of a proton on it. Mass of an alpha particle is roughly 4 times that of hydrogen atom. Velocity of alpha particles ranges between 1.4 into 10 to the power 7 meter per second to 2.1 into 10 to the power 7 meter per second. Beta particles are fast moving electrons. A beta particle possesses the negative charge of an electron on it. Mass of a beta particle is the same as that of electron, that is 9.1 into 10 raised to the power minus 31 kg. Velocity of beta particle ranges from 33% to 99% of the velocity of light. गामा रेडिएशंस सिर्फ एनर्जी रेडिएशंस होंदियां ਹਨ। ਇਹਨਾਂ ਰੇਡੀਏਸ਼ਨਸ ਵਿੱਚ ਕੋਈ ਪਾਰਟੀਕਲਸ ਨਹੀਂ ਹੁੰਦੇ। ਇਹ ਇਲੈਕਟ੍ਰੋਮੈਗਨੈਟਿਕ ਰੇਡੀਏਸ਼ਨਸ ਹੁੰਦੀਆਂ ਹਨ ਜਾਂ ਸਮਝ ਲਓ ਲਾਈਟ ਦੀ ਸਪੀਡ ਨਾਲ ਚੱਲਦੀਆਂ ਹਨ। Basic rules for such radioactive decays are simple. When a nucleus undergoes alpha decay, it transforms to a different nucleus by emitting a helium nucleus. Q value of an alpha decay can be expressed as Q equal to mass defect into C square. When a nucleus undergoes beta decay, the nucleus transforms into a new nucleus by emitting an electron along with an antineutrino particle. Here, Q is the energy released in beta decay. When a nucleus undergoes a gamma decay, daughter nucleus has the same charge number and same mass number as those of the parent nucleus. According to decay law, the rate of disintegration minus dN by dt is equal to lambda n, where lambda is called the decay constant or disintegration constant and n is the number of radioactive atoms at time t. Here, the negative sign shows that n is decreasing with time. On integrating, we get n equal to n0 e raised to the power minus lambda t, where n0 is the number of radioactive atoms at time t equal to 0. ਕਿਸੇ radioactive substance ਦਾ rate of decay ਇਸ ਦੀ half life ਦੁਆਰਾ specify ਕੀਤਾ ਜਾਂਦਾ ਹੈ, ਜਿਸ ਦਾ meaning ਹੈ ਉਹ time duration ਜਿਸ ਵਿੱਚ radioactive substance ਦੇ half atoms disintegrate हो जान. If the half life of a radioactive substance is T, then T is equal to natural log of 2 by lambda or 0.693 by lambda.
It is clear that after one half-life, the number of radioactive atoms decreases by 1/2. That is, the number of radioactive atoms left in the sample is N0 by 2. During the next half-life, the number decreases again by 1/2. That is, the number of radioactive elements left in the sample becomes N0 by 4. If we generalize this behavior of a radioactive substance, we can say that after n half-life, the number of radioactive atoms left in the sample becomes n0 into nth power of half, where n is the number of half-lives.
The average life of a radioactive substance is reciprocal of decay constant of the substance. Hence, average life period of a radioactive substance is 1.44 times the half-life of the substance. Let us now try to solve some numerical problems based on atomic nucleus and radioactivity. Calculate the density of iron nucleus in SI units. Mass number of iron is given as 56 and mass of iron nucleus is 55.85 atomic mass unit. We know that the nuclear density rho is equal to 3 Ma upon 4 pi A R0 cube. Here in this problem, mass of the nucleus is 55.85 atomic mass unit or 9.271 into 10 raised to the power minus 26 kg. We know that R0 is 1.1 Fermi, which is 1.1 into 10 raised to the power minus 15 meter. Therefore, nuclear density rho is equal to 3 into 9.271 into 10 raised to the power minus 26 divided by 4 into 3.14 into 56 into cube of 1.1 into 10 to the power minus 15. On solving, we get density as equal to 2.971 into 10 raised to the power 17 kilogram per cubic meter. In our yet another problem, you have to obtain approximately the ratio of nuclear radii of iron 2656 and uranium 92-235. What is the approximate ratio of their nuclear densities? Here, mass of iron is 56 and that of uranium is 235. Ratio of their nuclear radii is the cube root of the ratio of their mass numbers, which would be equal to the cube root of 56 upon 235, that is 0.61997. सारे न्यूक्लियाई दियां न्यूक्लियर डेंसिटीज सेम ਹਨ ਇਸ ਕਰਕੇ ਉਹਨਾਂ ਦਾ ਰੇਸ਼ੀਓ 1 ਦੇ ਬਰਾबर ਹੋਵੇਗਾ. Let us try some problems on binding energy. Calculate binding energy of helium nucleus. Given that the mass of helium nucleus is 4.002800 atomic mass unit. Mass of a proton is 1.007825 atomic mass unit and the mass of a neutron is 1.008665 atomic mass unit. One atomic mass unit is equivalent to 931 million electron volt upon square of speed of light. In the given helium nucleus, atomic number Z is 2 and mass number A is 4. Using the expression for mass defect and substituting the corresponding values, we get delta M equal to 0.030180 atomic mass unit. It means that the binding energy is equivalent to 28.097580 million electron volts. The next problem is calculate binding energy per nucleon of sodium nucleus. Given that the mass of sodium nucleus is 22.989898 atomic mass unit. Mass of a proton is 1.007825 atomic mass unit and the mass of a neutron is 1.008665 atomic mass unit. 1 atomic mass unit is equivalent to 931 million electron volt upon square of the speed of light. In the given sodium nucleus, atomic number Z is 11 and mass number A is 23. Using the expression for mass defect and substituting the corresponding values, we get delta M as equal to 0.200157 atomic mass unit. That means binding energy is equivalent to 186.346167 million electron volt. We know that binding energy per nucleon is equal to delta mc square upon A. On substituting the corresponding values, we get binding energy per nucleon as 8.102007 million electron volt. In another problem, you have to calculate mass defect and binding energy for lithium nucleus. Its mass is 7.000000 atomic mass unit. Mass of a proton is 1.007825 atomic mass unit and the mass of a neutron is 1.008665 atomic mass unit. 1 atomic mass unit is equivalent to 931 million electron volt upon the square of speed of light. In the given lithium nucleus, atomic number Z is 3 and mass number A is 7. Using the expression for mass defect and substituting the corresponding values, we get delta M equal to 0.058135 atomic mass unit. This means binding energy is equivalent to 54.123685 million electron volt. Our next problem is calculate binding energy per nucleon of calcium nucleus. Given that the mass of calcium nucleus is 39.962589 atomic mass unit. Mass of the proton is 1.007825 atomic mass unit and the mass of a neutron is 1.008665 atomic mass unit. 1 atomic mass unit is equivalent to 931 million electron volt upon the square of speed of light. In the given calcium nucleus, atomic number Z is 20 and mass number A is 40. Using the expression for mass defect and substituting the corresponding values, we get delta M as equal to 0.367211 atomic mass unit. This means binding energy is equivalent to 341.873441 million electron volt. We know that the binding energy per nucleon is equal to delta mc square upon A. On substituting the corresponding values, we get binding energy per nucleon as 8.5468 million electron volt. Let us have a look on some other types of problems. After a series of alpha and beta decays, plutonium-239 becomes lead-207. how many alpha and beta particles are emitted in the complete decay scheme. We know that when an alpha decay takes place, mass number decreases by 4 units and atomic number by 2 units. On the other hand, when a beta decay takes place, mass number remains unchanged and atomic number increases by 1 unit. Therefore, it's clear that the mass number decreases only in alpha decay. So, in this problem, the parent nucleus is plutonium 94-239 and the daughter nucleus is lead 82-207. In this decay, mass number has decreased by 32. Therefore, number of alpha particles emitted will be 32 divided by 4, that is 8. Again, because of the emission of 8 alpha particles, the atomic number should decrease by 8 into 2, that is 16. In other words, atomic number should have become 78. Since the atomic number of daughter nucleus is 82, it means the plutonium must have emitted some beta particles. And due to a beta decay, atomic number increases by 1 unit. Therefore, number of beta particles emitted will be 82 minus 78, that is 4. In our next problem, the half-life period of a radioactive substance is 32 days. What is the time taken for 7 by 8 of its original mass to disintegrate? If N0 is the initial number of atoms and after T days number of atoms become N, then it is given that N0 minus N upon N0 is 7 by 8. That is, N by N0 is 1 by 8. It is also given that the half-life of a radioactive substance is 32 days. Since N upon N0 is equal to small t by capital Tth power of half, that is 1 by 8 is equal to small t by Tth power of half, or small t by t is equal to 3. Then the required time would be 3 into 32, that is 96 days. Let us take another problem. A radioactive substance decays to 1 by 64th of its initial numbers in 30 days. Calculate its half-life. If T is the half-life of the radioactive substance, then N upon N0 is equal to small t by Tth power of half. Here, N upon N0 is 1 by 64, that is 6th power of 1 by 2. Since T is 30 days, hence 30 upon capital T would be equal to 6. On solving, we get T equal to 5 days. Hence, the half-life of the given substance is 5 days. The next problem is, after a certain lapse of time, the fraction of radioactive radium undecayed is found to be 12.5% of the initial quantity. Calculate the disintegration constant and the duration of this time lapse if the half-life of polonium is 140 days. Here, the half-life is 140 days. Since disintegration constant lambda is equal to 0.693 by T, the disintegration constant lambda would be equal to 0.693 by 140. This is equal to 4.95 into 10 to the power minus 3 per day. Furthermore, n by n0 is 12.5%, that is 0.125. We know that n by n0 is equal to e to the power minus lambda t, where t is the required time. On substituting the values of n by n0 and lambda, we get 0.125 equal to e to the power minus 4.95 into 10 to the power minus 3 times small t, or minus 4.95 into 10 to the power minus 3 into small t would be equal to natural log of 0.125, which is equal to natural log of 1 by 8. This is further equal to minus 2.303 into log of 8, which would be equal to minus 2.08. Hence, the required time t would be equal to 2.08 upon 4.95 into 10 to the power 3, which is 420.20 days. Another problem is the half-life of uranium-238 against alpha decay is 1.42 into 10 to the power 17 second. How many disintegrations per second occur in 1 gram of uranium-238? Given Avogadro number is 6.02 into 10 to the power 23 per mole. Here T is 1.42 into 10 to the power 17 second and Avogadro number is 6.02 into 10 to the power 23 per mole. 1 gram of uranium-238 contains 6.02 into 10 to the power 23 upon 238 numbers of atoms, which is 2.53 into 10 to the power 21. The disintegration constant lambda would be equal to 0.693 upon 1.42 into 10 to the power 17. This is equal to 4.88 into 10 to the power minus 18 per second. Since the rate of disintegration dN by dt is equal to minus lambda n, on substituting the values of lambda and n, we get dN by dt equal to minus 4.88 into 10 to the power minus 18 into 2.53 into 10 to the power 21. This is equal to minus 1.2346 into 10 to the power 4. It means that in 1 gram of uranium-238, 12,346 disintegrations will occur in 1 second. In our yet another problem, in an experiment, the activity of 1.5 milligram of radioactive chloride of isotope potassium-40 was found to be 175 per second. Taking molar mass of potassium chloride to be 0.075 kg per mole, find the number of half-life of potassium atoms in the sample. Here, molar mass of potassium chloride is 0.075 kg per mole and mass is 1.5 milligram or 1.5 into 10 to the power minus 6 kilogram. Since 1 mole of a substance contains molecules equal to Avogadro number, hence the number of molecules in the potassium chloride sample would be 6.02 into 10 raised to the power 23 upon 0.075 into 1.5 into 10 to the power minus 6, which would be 1.204 into 10 to the power 19. It is given that the activity of the given sample dN by dt is 175 per second. Since the rate of disintegration dN by dt is equal to lambda n or minus 0.693 upon n upon t. On substituting the corresponding values, we get 175 equal to 0.693 into 1.204 into 10 to the power 19 upon t. Therefore, half-life of the sample would be 4.768 into 10 to the power 16 second. आज दे टॉपिक ते ध्यान देण लई तुहाडा धन्नवाद. See you in the next class. Goodbye.